The Lenoir cycle consists of constant volume heat addition, isentropic expansion, and constant pressure compression. For the cycle, P1 is equal to 14.7 pounds force per inches squared, and T1 is equal to 540 Rankine. The mass of air is 4.24 times 10 to the negative 3 pounds, and the maximum cycle temperature is 1600 Rankine. Assuming that CV is equal to 0.171 BTU per pound times Rankine, determine the cycle for the net work in BTU and also the thermal efficiency. For process 1 to 2, we use the first law to determine that U2 minus U1 equals Q from 1 to 2 minus work from 1 to 2. There's no work in process 1 to 2 because the volume is held constant, so we can cross out work from 1 to 2. Process 2 to 3, again using the first law, we determine that U3 minus U2 is equal to Q from 2 to 3 minus work from 2 to 3. In this process, energy is rejected as work during the isentropic expansion, so we can cross out Q from 2 to 3. For process 3 to 1, again using the first law, we find that U1 minus U3 is equal to Q 3 to 1 minus work from 3 to 1. In this process, there is constant pressure heat rejection, so we can use work from 3 to 1 set equal to the integral P dV, which is equal to P1 times V1 minus P3 minus V3. And these B's are specific volumes. This Q from 3 to 1 is also equal to H1 minus H3, which then again is set equal to Cp times T1 minus T3. We can now go ahead and calculate the net work using work net equal to mass times Q from 1 to 2 plus Q 2 to 3 plus Q from 3 to 1. We can further reduce this equation by subtracting Q from 2 to 3 because the heat is rejected as work. And we can go ahead and further reduce this equation to where work net is equal to the mass times U2 minus U1 plus H1 minus H3 from the above equations of Q1 to 2 and Q3 to 1. With Q1 to 2 equal to U2 minus U1, we can also set that equation is equal to CV times T2 minus T1, and by setting Q31, which is H1 minus H3, equal to CP times T1 minus T3. We are given the value of C1, which is 0.171 BTU times Rankine. But we run into the problem because we are not given T3. We need to calculate T3 by using the relation equation in the book from chapter 6.43, which is equal T3 divided by T2 is equal to P3 divided by P2 to the exponent k minus 1 over k. With a given value of k equal to 1.4, we can now plug in our known values to solve for T3. We also need one last equation before we solve for work net, and that is Cp is equal to Cv plus R. R being within the units of BTU is equal to 1.9859 BTU divided by pounds mole times Rankine. With this given value of R and the given value of Cp, we can calculate Cp. After knowing the value of Cp, we can plug in the value for mass, the value for CV, also the values for T2 minus T1, and Cp, also the value for T1, and also the value for T3 to solve for work net. We next need to solve for thermal efficiency. The thermal efficiency is equal to work net divided by Q from 1 to 2, where Q from 1 to 2 is equal to mass times CV times T2 minus T1. Once we calculate Q from 1 to 2, with the known values. We find the thermal efficiency to be 16.2%.